start the second session this afternoon. We will have 7 presentations in the session. We hope we can close the session 5:40, each in 15. Please take care time. Okay, first one. Sorry, I missed the program. Okay, first I'd like to invite Shervin to give her first talk, please. So let's welcome. Oh, is this one? Control L.
F5. Those.
Yeah, this one.
It was already open somewhere else as well. Here. Someone
Control L. Control L. Yeah.
No link? Now it works. Okay. Thanks. So good afternoon. In the next 10-15 minutes, I will be fascinating you with the digital twin that we are developing at the ILL. Everything started with the idea to enrich the offer of user tools with the possibility to run also virtual experiments here at the ILL. And this is something that can be brought everywhere at any facility. The idea is the same, and the fact that could be useful for training for newcomers that might need to learn the instrument control system, or users that want to move to a different instrument that they have never used to get familiar with its configurations and capabilities, or digital twins could be used as well as setting optimizations for a particular instrument, studying some settings, or even at analysis level, whenever we might need to better understand some of the background sources and their effects and uncertainties on the analyzed data, not last support material for proposals whenever someone wants to apply for some beam time. So there is a broad number of opportunities coming up with having a digital twin implemented. And in order to have it done, we also fixed some design requirements that, first of all, the digital twin should hide the complexity of the simulation. And so it targets users with basic knowledge or no knowledge in neutron racing, for example, interaction simulation. The idea of having everything hidden is letting the user interface to be the same as the data acquisition one, so a familiar interface, and such that they can prepare their workflow as they are used to. And the simulated data should not be something else with respect to what they are used to in the real data. So the idea is to have the simulated data processed by the instrument control system such that they provide exactly the same format to the user, such that it can undergo further analysis, so reduction and analysis workflows. In order to perform this simulation, we need to run state-of-the-art simulation softwares. Here at ILL, we have chosen to start with Maxtas, as you have heard before, for neutron ray tracing. But of course, the digital twin allows that to be a pluggable thing based on the needs. So everything starts for the user from the GUI, of course. And as you can see, the user seated in front of their screen, they interact with this GUI that you see on the left. And it's basically a Java client here at ILL that connects to the Nomad server that is the real instrument control system core that is in C++. And everything is done essentially in the server. And from the GUI, the user can set a workflow, as you can see in this slide, with fixing the instrument settings and starting the counting for a given time or with scans, so on and so forth. So this is what they can do for the rear instrument. For having a digital twin, we needed to add an additional module on the server side. And this simulation module, you can see what happens in the GUI. You have an additional flag. And for the user to set up whatever is not present in the real data, so the information about the sample. So you have an additional tab where the user can enter whatever they know about the sample that they want to simulate, so the shape, the size, the material, and they can provide that for the sample as well as for the sample holder to have some artifacts of the background coming from that, for example. And they can select it from a predefined list of something that we have already entered, but they can also provide in the Maxas format currently as of Q omegas for samples that they have simulated somewhere else in DFT, so on and so forth. And what happens is that they define their workflow, and they can start the acquisition, pushing the play button, simply as that. They can follow the simulation happening with the bar at the bottom or the blue bar progressing through the workflow, the entire workflow. And they have a live feedback of what happens in the simulation, so they do not have to wait till the end of the simulation to have something. It updates progressively, as you can see, and till the end of the simulation. So they get these refreshes at fixed times with increased statistics. So they can even stop the simulation whenever they are fine with what they see and start something else, getting the data, as they would do on the real detector. And what you can see here is an example of the results. For example, on the left, there is the D11 instrument with the real data of some sample that is used for the calibration of the instrument, and at the bottom it's corresponding simulation done with using the digital twin and getting the results in Nexus format. So this is a view with Silex. On the right, you can see some more advanced, if you want, data acquisition, a scan over one axis of a triple axis instrument. As you move the axis of the instrument, you take several data acquisitions, and each point here corresponds to a different simulation with the given parameters. So everything is completely hidden, so the user starts a scan on the interface, and they get the scan plot at the end. So they do not have to do something different to what they are used to. What would be a digital twin without a view of the detector? So imaging for training, but not only that, people would like to see how the instrument looked like and what those parameters correspond to the real detector. So they have this 3D view that is built from a solid works of the instrument, and it's not a fixed view. This is a live update, a 3D live update, where they can see the current configuration that they have set up on the GUI. And if they are changing the settings, they could also see the moving parts moving. So they could also follow what is really happening, changing the configurations. So the entire system is structured in this way. There are 4 main components for the digital twin. One is C++ client API that is used in the simulation module in the data acquisition system. And this client API is responsible to create the simulation request and sending it to a simulation server. So the simulation server replaces the instrument hardware. So what happens is that in the Nomad server, in the instrument control system, instead of sending the information about the axis, positions, motors, so on and so forth to the hardware, it sends this simulation request to the simulation server. So everything about the instrument is there, plus the information about the sample. The simulation server packs and dispatches as many parallel workers that are needed to perform the simulation, and this is now performed on the HPC using SLARM. So we are parallelizing these simulations, and each worker is running a complete independent simulation using Maxas in this case, and they return the result to the server, and the simulation server backs to the instrument control system. And the fourth component is the 3D viewer, as I've shown you. What this complex system is managed by the Cameo middleware, and there is a poster about, from Yannick Legoc that you can see upstairs. And the Cameo is managing the different applications, starting and stopping also on remote machines, and this is what happens. The Nomad server is one machine, the simulation server is somewhere else, and then there is the HPC. And the communications between these applications is managed by Cameo as well, with a high-level abstraction with the publisher, subscriber, requester, responder schemes. What happens on the workers? So the workers are running a program of the simulation. This is, as I said, a Maxas compiled binary. The description of the instrument, we have chosen to build upon what was done in Panosk, and essentially describing the instruments in Python using Maxas script and the libpyvinyl library, and storing them on a GitHub public repository of the Panosk vinyl repository. And there you can have as many instruments that you want from your institute. You are not obliged to have descriptions that can go with this digital twin, because they are described using the libpyvinyl library, so you can even use them outside of the digital twin with a Jupyter notebook to test them, to modify them, so on and so forth. And instrument executables are essentially taking the description from the instrument repository, compiled, and we compile them both for CPUs and GPUs, prepare these binary packages, and ship them to the HPC nodes in order to have them executed. So in summary, the objectives that we have achieved are, we have built a good prototype setup for the digital twin with the different elements that we think are really needed. This digital twin can be used by users, actually, that have no knowledge about the simulation, because everything is behind the scenes for them. And the data that they get has in the usual format, and they can undergo reduction and analysis workflows. We have adopted the client-server model in this case, and because this is flexible enough to get new interfaces, for example, for the simulation server, that we can send or ask new simulations not only from the GUI or the system software, the instrument control system, but we could also ask simulations from a Jupyter Notebook via a Python API, for example. We achieved the parallelization using a cluster here with the SLARM, and this is implemented and working fine using both CPUs and GPUs. And the workers are flexible enough to allow different simulation software to be used instead of Maxas. And finally, a 3D live view that we think it's really useful for everyone to understand what is happening at the instrument. There are a few further steps that we foresee, adding, for example, non-simulated background from real data, because simulated data are always limited by the model that we have described, so there are some background sources that we cannot model. And develop also surrogate models with machine learning in order to accelerate the simulation process with different steps. Thanks.
Thank you. That's very interesting. And I'm wondering, SolidWorks is proprietary and quite expensive, from what I know. Is there a possibility to export these models and then handle them in, let's say, Blender or some other open source?
So it's not. I mean, what I said about SolidWorks is that the original model that we had is from SolidWorks. Then there is a huge amount of work in order to get that out of SolidWorks reduce the model, because the model from SolidWorks usually is too complex with respect to what we want to see. So there is a refinement process that is quite complex. And on that model, we have also to add the translation and rotation of the different elements. So grouping, editing, this is part of the process to have a simplified model with a specific language that we have in-house, such that we can show the 3D in a web page, because this is done lively in a 3D in a web page. So if you have a model from somewhere else, you can undergo the same process and get the viewer.
Yeah. So I think I saw there was a triple axis there, and there was D11. Is this something that is planned for any instrument in production at the ILL? Or?
So this is under development, so nothing is in production now. And we have a third instrument that is a TOF, Panther, that is being under my hands since a little bit of time. There are quite a bit of tricky things for TOF detectors, because Maxus do not natively have the capacity of having a 2D detector with TOF capabilities. And so there are some things that we have done in order to get that. But it's a little bit more complex in the sense that the simulation, it gets longer than what happens, for example, for a triple axis. So.
Sure. I have a 3D format for you in Nexus, actually, that would take that. Anyway, we can talk
would
about
have been even better to have it before.
I know, sorry.
Last question.
Thanks for a really interesting talk. Yeah, we've also tried sometimes to have some simulated representatives of our beamlines and stuff. But one problem that we run into often is that the hardware on the beamline changes faster than we can keep our simulation up to date. Is that a problem that you face? Do you have anything to make it easier to do that? Just interested in thoughts in general.
So for ILL, the instruments are not changing that fast. So they keep running for years. But as I was saying, the description here is done in Python. So in this case, because we are using this libpyvinyl library with MaxaScript, if you know what you are doing, so if you know how to describe the instrument with MaxaScript, in one day you can describe a new instrument. Especially if you have already elements, so you're not starting from zero. One of the difficult things is to get from the scientists on and so forth, what is the exact distance between this module and the other? Once you have this information, coding is not that much of a trouble. And one thing that I want to stress, in this kind of database, one thing that we have thought about when designing the database is that if you see here, there is a head in the tree structure. Head is the most recent version of the instrument. So you can have multiple versions of the instrument, and that is especially interesting if you want to run a previous version, because you have data acquired 2 years ago, and the instrument went under an upgrade in the meanwhile. So you can retrieve the previous version of D11, for example, and run the simulation with that. So it is already designed in order to be able to follow the upgrades of the instrument.
Okay, I'm afraid we have to move on. Okay.